So thanks to the organizer for this wonderful week that we are attending now, and thanks for letting me speak this afternoon. So the theme of this talk is left-handed flows. So left-handed flows is a notion introduced in 2008 or 9 by Etienne Ghys, and the motivation for this notion comes from this picture here. So this picture represents a flow, well, some orbits, some periodic orbits actually, of some flow in R3, which is called the Lorentz flow. I'm not going to speak too much about this flow, but so this flow has the property that it has many periodic orbits, for example, the red here, that winds around both ears of these attractors, longer periodic orbits like this orange one, which is very long. And so this flow has many periodic orbits, and Ghys in this started to study the periodic orbits of this flow. Well, actually, it's not the one we started to study them. These studies were initiated by Birman and Williams in the 80s. But what we observe here that we have many periodic orbits which form many knots in the 3 space. And the question is, what can we say about these knots? And in this particular example, we can observe a very peculiar property. If we observe this knot, and we look when 2 such knots project to the same point with this projection. So when do we see a crossing between 2 orbits? For example, here we have the red orbit here, yes, and behind we have the green one that comes from the left. And if we orient these knots, we see that all crossing that we can see are what is called negative crossing in knot theory. That means that the right strand goes in front of the left one. And for all crossing that we can see on this picture, we have this phenomenon that the right strand goes in front of the left one. And so from the point of view of periodic orbits, this tells us that all linking number that we can compute between periodic orbits here will be negative. So linking number, I will speak of that later, but this is a knot invariant. And this is a very, well, exceptional phenomenon. I mean, linking number could be positive, negative, and if we have many knots, we could expect some of them to be positive, some of them to be negative. And here, it's always negative. And this is where the notion of left-handed flows comes from. So this notion introduced by Ghys in, 2009. This is a flow which will have this property. So the first half of the talk will be about left-handed flows, and to tell you why this notion is interesting or could be interesting. And then the second half of this talk will be devoted to examples. So we have this nice property, and well, when it was defined, there was only 2 examples of such flows, this one and an even simpler one, the Hopf flow. And so the question is, if we have such a nice notion, do we have other examples? And we'll see that it's natural to conjecture that geodesic flows are left-handed, and there are many geodesic flows. And so it's the goal of the talk to answer this question. I can tell you in advance that the answer is not always yes. The answer is it depends, sometimes yes, sometimes no, and we will see some examples. Okay, so the starting point to see why left-handedness is interesting is to recall was a global section for a 3-dimensional flow is. So we start with M, a compact 3-manifold, and X, a non-singular vector field in M. And now, well, we define the notion of section. So we say that a surface S is a section, and we emphasize that it's a global section. If, well, informally speaking, if S allows to reduce the dynamics of the flow to the dynamics of some first return map on S. So for that, we need 3 conditions. Well, first, S should be a compact surface with no boundary. Then we ask that S is transverse to the vector field So here X, I should have said X is a non-singular vector field. Yes. And the important thing, we ask that every orbit of the vector field intersects S after a bounded time. Okay, so oops. Well, it means that for all, yes, uniformly bounded. Yes, uniformly. Oh, okay, so this goes too fast. Yes, so here is a section. So we have a vector field, I didn't draw it. And here we have a surface. Okay, and here for any point here, we know that after some time, if we follow the flow, we'll come back onto the surface. And we know that the time here is uniformly bounded. And if we go backwards, actually, we know that, well, since the first return time is uniformly bounded, we cannot avoid the surface if we go in negative time. So we know that every arc of orbit can be, well, from every point, we can go backwards, meet the surface, and go forward and meet the surface again. So what we observe here then is that if we have such a global section, now if we cut M along this global section, what we get, well, so if we just start from N and push a bit, we obtain something which is, if we start from S, we obtain S, and then if we follow the flow, we are just pushing S, okay, and then we will fill the whole manifold until we come back here. So here, this is S cross 0 corresponds to the upper face of the surface, and S cross 1 to the bottom face, and then we obtain everything. And here we have more. We have that here the vector field here is sent just on the vertical vector field d over dt. So here, actually, when I say that here, this is up to reparametrization of the vector field, I say that the first return time is bounded, so I can change the time variable so as to make it 1. For every green point here on the surface, you can assume that you come back here after time 1. Okay, and now if we glue back S, what we have to do is to glue back S on both sides. So we glue back 0 and 1. And just we have to identify the top and the bottom face of M. And so this means that we identify a point X with its image by a first return map. So here, this is just the map that sends the green star on the blue star. So F is the first return map. So from the dynamical point of view, this is interesting because it reduces the dynamics of the flow X to the dynamics of the first return map here, F. So we went one dimension down. So if we can find such a section, we are happy. We have reduced the dimension of the problem of studying the dynamics of the flow. So now the natural question, of course, is which flows admit global sections? Well, the sad thing is that actually this is often a negative answer. For example, assume that we have a flow in S3, for example. Then a section should be an embedded surface, so it has an outside and an inside. And if the flow crosses in one direction from the inside to the outside, then it stays in the outside and it cannot come back. So actually a flow in S3 cannot have a global section. But, okay, so we need more than, well, still, there is a nice theory that I want to briefly explain of which flows admit global section, and this will be of use later in the talk to understand the notion of Birkhoff section. So the idea is that when a flow has a global section, so assume that S is a global section, So S is an embedded surface. Then for all gamma, say, periodic orbits of the flow, so assuming we have periodic orbits, but this is not the point here, for all gamma periodic orbit, we can look at the intersection between the surface S and the orbit gamma. And what do I mean by intersection? I mean that the surface S is oriented. Yes, so a small orientation. And the flow is transverse to it. So when we have that, an oriented surface and a vector here which is transverse, the intersection can be positive or negative. And so here, well, I didn't make any assumption, but up to changing the orientation of S, all the intersection points will be of the same side, of the same sign. So what we will have is that for all S and for all gamma, the intersection will be just the number of intersection points with signs will just be positive, because all intersection points will be positive. So we can assume that, well, no, we cannot assume that, we have that. And now we can look at the intersection in homology between our surface S and the class of gamma in homology. Yes? And this is just, well, this is just the same thing, because what we defined was actually an homological intersection. So what we get is that for all periodic orbit, the intersection between the class of S, which is an element of the H2 of our manifold, and the class of gamma, which is an element of the H1. So here, this pairing is positive on all periodic orbits. So if I imagine that here is H1 of M, yes, so let's assume it's two-dimensional, we can draw the class corresponding to periodic orbits. So here, gamma 1 is a periodic orbit, gamma 2 is a periodic orbit, gamma 3 is a periodic orbit. And we can draw the one form defined by the intersection with our surface. So here we have our surface, which defines an element in H2, so by duality, a one form. And so here I draw the kernel of this one form. So this here, this half plane corresponds to intersection with S positive. And what does this remark say is that for all periodic orbits, the class of this periodic orbit here is in this half space. So if we have a section, we have that the class of the periodic orbit lies in some half space. Yes. Yeah. Well, because we are transverse to the flow. So since we are transverse to the flow, if you look at the surface, at some point the flow is transverse, say, in the positive direction. Then on the whole surface, it has to be transverse in the positive direction, because it cannot become tangent at some point. If it was sometime positive, sometime negative, in the middle it should be tangent at some point, and this is not possible. Yes, I should have said that S is orientable. Yes, actually, yes, this comes from the third condition, but maybe we should also add that this is connected. Okay. So here, well, if we have a surface of section, we have that the class in H1 of all periodic orbits lies in some half space. Well, of course, if we have no periodic orbits, say, this condition says not much. So actually, we have something a little bit stronger. We have that actually all asymptotic cycles lies in some half space. So what is an asymptotic cycle? The thing is that, well, a periodic orbit is a restrictive condition. And say we start from a point X in our manifold M, we can follow the flow for some time. So say we follow the flow of X for some time t. Yes. And we have, well, if the orbit is not periodic, we have no reason to come back. But what we can always do is to join this extremity here to our initial point by some segments, say, of bounded length. So since we have a compact manifold, we can always join by a segment of bounded length. And this gives here a chain, a one chain. So this gives a closed curve that I denote by k of xt. Yes, and we can look at the class, the homology of this curve here. Okay. And the idea is that if we iterate that for long enough, we can look at the class k of xt, okay? And we can look what happens when t tends to infinity. Well, actually, if we want to define that, we have to renormalize. And the statement is that this limit here exists for almost every point, for almost every x. Okay. So here we have, this is a limit which exists in H1. Okay. And this is called a Schwarzmann asymptotic cycle. So of course, if x was a periodic point, this limit coincides exactly with the class of the periodic orbits up to the period of the periodic orbit. But so this class is well defined for almost every point. And the same argument, since if we have a section S now, still all intersections will be positive, except maybe those of this green arc. Yes. But in the limit, this green arc has bounded length, so actually the contribution of these green arcs disappears in the limit. And so for all asymptotic cycle, we have also that the intersection is positive. So we also have that the intersection between S and the cycle that I will denote Cx is positive. So here this gives me more points. Okay. And so we have many things. And now we can look at the set of asymptotic cycles. So this set is denoted by S. So it depends on the vector field. So this is the set of asymptotic cycles. Yes. And so here the statement is that if S is a section for S, a global section for the vector field X, then this set of asymptotic cycles is included into some open half space. Yes, it is included in the open half space defined by intersection with S is positive. And now the wonderful theorem that was first proved by Fuller in '67, and well, in another form by Fried in the '80s, is that this is an equivalence, actually. So this set is actually compact and convex. Yes. So saying that it is included in some open half space is equivalent to saying that 0 is not in this set. So we have that X admits a global section if and only if S of X does not contain the origin. So this is a set in the H1 of our manifold, and we have this criterion here. So in particular, well, we find again what we have seen. In S3, well, there is no homology, so of course the only point in S of X is 0, since it's the only point in H1, so any flows in S3 cannot have a global section. Okay. So I'm not going to prove this theorem, but, well, just give an idea of the proof that if you have your set S of X here in some open half space, you can find a class here. Well, we can find a one form which will be positive here. And then what you want to do is to represent this one form by a surface that will be transverse to the flow everywhere. So this statement here tells you that if you take a surface that realizes this class, ultimately, if you compute intersection, they will be positive. But it doesn't tell you that everywhere the intersection will be positive. It can be sometimes positive, sometimes negative, but ultimately, if you compute on long arcs of orbit, it will be positive. And so actually what you can do is to average in one form. So here, this class is actually defined by a one form. You can average this one form in order to get a one form which is positive everywhere, and then take a level of this one form from your surface. Okay, this is just a sketch, but just that this surface S here can be effectively constructed once we have this Schwarzman set, the set of asymptotic cycles. Okay, anyway, here we were interested in flows in R3, if we think about the Lorentz flow. So this definition is not satisfying since we cannot apply it. And so we have to modify it a little bit to introduce the notion of what we now call Birkhoff section. So what is a Birkhoff section? A Birkhoff section will be almost the same thing as a section, except that we allow the surface to have boundary. So here, the surface we have, so here is what is different. The surface can have boundary, just we will add a condition. I will put it here, a fourth condition here, that the boundary of S has to be tangent to the flow. Okay, so if we have a compact surface with boundary, the boundary is made of circles. So if we want this boundary to be tangent to the flow, this means that the boundary is a finite collection of periodic orbits of the flow. So here we ask that the boundary is a finite collection of periodic orbits. And now, so in particular, the boundary is not transverse to the flow, but we ask that the interior of our surface is transverse to the vector field. So what we want is that the interior is transverse to the flow, and now every orbit, well, should either be in the boundary or should intersect the interior of our section after a uniformly bounded time. So the picture is almost the same, except that this time we allow a surface with boundary. Here we have one boundary component, yes, so that the flow can go here from one point, if we follow an orbit, and then to the other side of the surface. Just our surface has boundary. Yes. So maybe this sounds a bit strange to say that the boundary is tangent to the flow and the interior is transverse, but this is not possible. This is not impossible. If you imagine that your flow, for example, is vertical, you have to imagine a surface that spirals around the vertical direction. So the vertical direction is in the boundary, and then if it spirals, every other point of the surface is transverse to the vertical direction. So this is not a problem here. And so, well, here we have a Birkhoff section. So why do I say that this is as good as before? Because this time, what we can do is once again cut along our section. So when we cut along the section, in the complement, what we obtain, if we push the surface a little bit by the flow, we still obtain the same surface, just pushed a bit by the flow, except that the boundary is fixed. So if we remove the boundary, what we have here is the interior of the surface cross 0, 1. So if we remove the surface and its boundary, we just push a bit, we have the interior of the surface cross 0, 1. And now when we glue back the surface, what we have, well, if I glue back the interior of the surface, I have, so now I just look at the complement of the boundary of the surface, and I have to glue back the top face and the bottom face. So here I get the interior of the surface cross 0, 1 modulo a first written map. So here, if we have a Birkhoff section, we have that we have reduced the dynamics of the flow outside the boundary to a first written map on the interior of the surface. So from the dynamical point of view, if you allow to remove finitely many periodic orbits, you have the same dynamics as a first written map. So once again, you reduce the dimension of the problem. Okay. And now the question is, which flow admits Birkhoff section? Do we have more examples For example, in S3, if we look at standard flow, do we have Birkhoff sections? And the answer is luckily yes. We have many examples that time. So which flows admit Birkhoff sections? Well, we can look at maybe standard example of flow. One very standard example of flow of non-singular vector field is what is called here the Hopf flow. So the Hopf flow on S3. So this is defined, so if we see S3 at the unit sphere in C2, this is just the flow whose orbit follow great circle, so yeah. So this, if lambda mu are a point of S3, this point is still on the unit sphere in SC2. So this describes orbits of some flow in C2. And what we see here that all orbits are periodic with period 2 pi. And if we make a drawing, like here Benoit Klockner did, we see this picture. So we have periodic orbits, which are just great circles. And now, does this flow admit a Birkhoff section? Yes, it does. So what is a Birkhoff section? Well, you can just take, for example, this red circle in the center here. These red circles bounds a disk that you see. And actually, this disk intersects all other orbits. So here, this disk, so we have a disk, and this disk is a Birkhoff section. And actually, the first written map on this disk, so if we start from a point on some orbit, for example, here in the center, we follow a great circle here, and we come back exactly at the same point. So the first return is the identity map. Okay. So we can look at other flows. For example, we can change here the parameters. We can put some parameters alpha, beta, which means that we rotate on both coordinates, but at different speeds. Yes, so here is a picture, for example. Here is a picture with alpha equals 3 and beta equals 5, for example. So you travel, and once again, you can foliate S3 with tori, and your flow stays on each tori. So you have infinitely many toris like that. And once again, if you take, there is a central orbit here, which corresponds to mu equals 0. So there is a central orbit here. And the disk bounded by this disk, by this orbit, is a Birkhoff section. And the first written map in this case will be a rotation of the disk. Okay, so here we have examples on S3 of flows with Birkhoff section. But now we can care about the second part of the title of the flow and come back to actually the first example of a Birkhoff section, which was constructed by Birkhoff. So it was in 1917. So Birkhoff was actually considering the geodesic flow on a sphere. So on a sphere with any metric, actually. And Birkhoff wanted, so in this case, the unit tangent bundle to the sphere is not S3. It's actually, so if we take a sphere, the unit tangent bundle is actually SO3. Okay. But still, in this manifold, we can look for Birkhoff section. And here comes Birkhoff construction. So here we have a sphere, which is round in this case. And we have a periodic orbit here, a simple closed geodesics. Yes. So what Birkhoff did was to consider a simple closed geodesics here. And this geodesic can be traveled in both directions. Yes. So if you lift that to the unit tangent bundle, so which is represented above here, what you get is two orbits of the flow, one which corresponds to traveling the geodesic in one direction, and the other one which corresponds to traveling the geodesic in the other direction. Yes. And now what Birkhoff does is to look at all tangent vectors that point on one side of this orbit. So this defines above every point here of the closed geodesics, you have an interval of tangent vectors. Yes. And now if you take any geodesic on the sphere, here suppose it is round for the moment, if you take any closed orbit, any geodesic on the sphere, at some point it will cross the green one and it will go from the left part to the right part. Which means that if we lift that to the unit tangent bundle, we'll intersect this green ribbon. So what Birkhoff says that here this ribbon, which is actually an annulus, it's a circle across an interval, this annulus here is a Birkhoff section. Yes. So what Birkhoff says is that here, if we have a geodesic, a closed geodesic, here, if gamma is simple and intersects every other geodesics, then Birkhoffs associate an annulus, which is a Birkhoff section. Yes. Okay. Yes. So actually, Birkhoff's remark also that it's not mandatory to have a simple geodesics or just one geodesics. Actually, it gives a more general construction that start from any, you could add other geodesics, other closed geodesics, or non-simple geodesics, and you could still play the same game. I will not describe it, but Birkhoff's remark that here, starting from any finite collection of closed geodesics, which have the property that they union intersect every other geodesics, he constructs a Birkhoff section. So Birkhoff remarked that not only we have one Birkhoff section, but we have many of them. Okay. Actually, what Birkhoff did, he did even something more. He did remark that even in higher genus, you can construct such sections. So here, for example, on the genus 2 surface, you can find some closed geodesics. So there are 6 of them. One that, well, it's not one, this one, then this one, then this one here that comes back behind, this one here, and a big one that makes the full turn. So you can take a collection of 6 closed geodesics, and the union of these 6 closed geodesics will allow Birkhoff to construct a Birkhoff section. So Birkhoff's construction, Birkhoff showed that actually every geodesic flow on a negatively curved surface admits a surface of section. So up to removing a finite collection of periodic orbits, Birkhoff reduces the geodesic flow to just the suspension of a diffeomorphism of a surface. Okay. So Birkhoff showed that a lot of flows admit Birkhoff sections, and actually there is a, I want to quote this theorem by Fried once again. Fried showed that actually, so in this around the same time, Fried showed that actually every transitive another flow admits a Birkhoff section. So in this setting, this generalizes Birkhoff section. So Birkhoff's result, Birkhoff say that for all negatively curved surface, we have a Birkhoff section, and the geodesic flow on a negatively curved surface is an example of a transitive another flow. But here, this theorem works for any transitive another flow. And I take this opportunity to recall another question that Fried asked, that here Fried's construction constructs a section, so which is a surface, and the surface has a genus. And if your surface has small genus, then the first written map is a diffeomorphism of a surface with small genus. You expect it to be simple. And Fried asked the question, can we always have a section, have a Birkhoff section of genus 1? So the first question would be, can we always construct a Birkhoff section that will be of genus 0, a puncture sphere? But here the answer is no. And here, for example, if you look at Birkhoff's construction, well, you have to, I didn't detail it, but if you look at this construction, the section Birkhoff's constructed is a torus with punctures, so it has genus 1. And Fried's construction is more abstract, so it just gives you a section with no control on the genus, and it is still unknown whether we can construct Birkhoff sections of genus 1 for any transitive another flow. Okay. Okay, let's come back to left-handedness. So let's just use this criterion illustrated here to see when we can find a Birkhoff section. So the next question, we have seen examples of flows with Birkhoff section. The next question would be assume that gamma is a periodic orbit of a flow. Yes. Does gamma bound a Birkhoff section? Does gamma bound a Birkhoff section? Yes. So for example here, Birkhoff showed that here, if you have a closed simple geodesics here, you take the union of two closed geodesics, this bounds a Birkhoff section. And generally, could we have a criterion that tells us, here is a periodic orbit, does it bound a Birkhoff section? Or here are three periodic orbits, do they together bound a Birkhoff section? And well, and the answer is more or less the same as for section. We can just apply what we say for section. So if S is a Birkhoff section, once again, we have that the intersection of S with every other orbit will be positive. Yes. Just we have a new remark here, is that if gamma is, say, a closed orbit, and S is a surface bounded by gamma, maybe with genus and so on. Yes. What is it? So here we have S. What is the intersection of S with gamma? Where here, this is exactly, by definition, the linking number of the boundary of S with gamma. So maybe I should define what is linking number. Linking number is defined in a manifold that is a homology sphere. So here I should add an assumption. We will also assume here that M is a homology sphere, so a rational homology sphere, which means no H1, no H2. Okay. In this context, when we have two closed curves, say K1, K2, yes, since we have no homology, no rational homology, we know that up to a multiple, K1 bounds a surface, S1. Yes. So we can look at the intersection between this surface and K2. Yes. And now the assumption that we have no H2 will tell us that this number of intersection does not depend on the choice of this surface. So linking number is defined if we have these two assumptions, and it's just the intersection between a surface bounded by the first closed orbit with the second closed orbit. So here, this intersection is exactly, by definition, the linking number. And if we have this assumption, this linking number is a well-defined function. Okay. Yes. So here, if gamma bounds a Birkhoff section, then we have that this linking number here, well, I shouldn't write it this way. I should write here K2. Yes. So if gamma bounds a Birkhoff section, gamma is the boundary here, and we have that the linking number with any closed orbit is positive in this case. Yes. And actually this will be an equivalent. So exactly as with Fuller-Fried, here we have an equivalent that gamma bounds a Birkhoff section. If and only if, for all asymptotic cycle, the linking number of gamma with the asymptotic cycle is positive. Okay, so this theorem is exactly the same as there, but here we have a criterion for an orbit to bound a Birkhoff section. Okay, and this is what led Ghys to define the notion of left-handed flow or right-handed flow. Let me define right-handed flow. So a flow X, well, a vector field, well, X is right-handed if for all asymptotic cycle, for every pair of asymptotic cycle, the linking number between these two cycles is positive. So here, well, actually, we define linking number for closed orbits, and asymptotic cycles are not necessarily closed orbit, but you can define that at the limit. And so we say that the flow is right-handed if and only for all cycles this linking number is positive. Yes. So I spoke a lot about, I said that we are looking for left-handed flows, and here I define right-handed flows. And actually the difference is that here there was a convention that we decided that the surface we could always orient it positively with the flow. But actually a surface has also an orientation that comes from the orientation of its boundary, and the orientation of the flow defined by the transversality to the flow and the orientation defined by the orientation of the boundary need not correspond. So actually it could also be the case that all linking numbers are negative, and in this case we'll say that the flow is left-handed. Okay. So why this definition? Because in this case, when we have such a flow, we can specify this to one asymptotic cycle, and then it's just an easy corollary that then if X is left-handed or right-handed, then every periodic orbit bounds a Birkhoff section. Yes. And actually it's not only every periodic orbit, actually it's then every finite collection of periodic orbit bounds a Birkhoff section. So in this case, we not only have one Birkhoff section, we have as many Birkhoff sections as we want. You take any number of periodic orbits, you get a Birkhoff section. So if we come back, for example, to the previous two examples. Oops. No. Yes, to this flow. Here, we have this property. Any two orbits are positively linked. So actually, any two asymptotic cycles are positively linked. And then this implies that any finite collection of periodic orbits bounds a Birkhoff section. So in this case, we have a maximality assumption. And then, well, so here we have this thing. And this thing explains the original picture. So here, in this case, we also have this property that any two periodic orbits are actually negatively linked on this picture. And so we have this interesting property that then if you take any finite collection of periodic orbits, for example here the green one and the red one, together they bound a surface which will be a Birkhoff section. So this reduces the dynamics of this flow to a first return map, and this is for all possible choice of finite collection of periodic orbits. Okay. So once we have that, we wonder, well, do we have many left-handed flows? And, well, actually, yes, we have. And actually, Birkhoff's argument gives good hope to show that geodesic flows are left-handed. Because Birkhoff's argument started with any collection of periodic orbits and associated a Birkhoff section. Okay? So, following Birkhoff, we could think that then every geodesic flow is left-handed, but actually there are two obstructions for that. Well, actually they are the same. The obstruction is that in general, the unit tangent bundle to a surface is not an homology sphere. So in general, this is not a homology sphere. So in particular, there will exist correspond of periodic orbits here that will not even bound a surface. Yes, you can take geodesics which are not zero in homology, and then if you lift them, you will get orbits which cannot bound even a surface, so a fortiori, they cannot bound a Birkhoff section. So actually, Birkhoff's construction started from a geodesics, and it took the two lifts. It lifted in one way and in the other way, and then it studies a surface is bounded by the two lifts of one geodesics. So here, Birkhoff's arguments actually tells you that if you take any collection of periodic orbits of the geodesic flow that is invariant by orientation changes, which means if you have a geodesic, you have the other one which corresponds just to the same geodesic in the other way, yes, then every such collection will bound a Birkhoff section. But this is not every collection. This does not correspond to any asymptotic cycle. So it tells you that you have good chances that this flow is left-handed, but this argument is not sufficient. Okay? And actually we can construct, I would like to describe first a counterexample where this is not the case. When we don't have left-handedness, this will correspond to a sphere here, a round sphere, with geodesics that do not intersect. So here, if you take a sphere that admits two non-intersecting geodesic, yes. Actually, you can show that the linking number between these two geodesics will be, for example, here, well, you have to make the computation. Here, the unit tangent bundle to a sphere is SO3, which is S3 mod out by Z over 2Z. So this is an homology sphere, but sometimes this means that every curve here bounds a surface up to a multiple. This is a rational homology sphere, but sometimes you have to multiply a curve by 2 to make it bounce. In particular, here, this curve lifted to the unit tangent bundle does not bound a surface, but if you consider it twice, it will bound a surface. It will bound a surface that can be represented as actually a vector field on the surface. Okay. And if you draw this vector field, it will fill the surface, and actually it will intersect this orbit in one point. So what you can get from this computation I did not really explain is that here the linking number between these two orbits of the geodesic flow is 1/2. Okay. And now the thing is that if you reverse the orientation of this geodesic here, you will get almost the same thing, except that the linking number will be inverted. So here what you get is that the linking number of gamma 1 with minus gamma 2, which corresponds to lifting these geodesics but in the other way, is minus 1/2. And so here, well, the sign is not always the same, so this flow cannot be nor left-handed nor right-handed. Okay. On the other hand, if you have a metric on the sphere such that any two geodesics intersect, then the geodesic flow on S2 with this metric is left-handed. So here we have two things. I will not prove that one. But here we see that in some cases, if the metric is not round enough, the flow is not left-handed. But actually, if the metric is round enough so that any two geodesics intersect, then the flow will be left-handed. Okay, so this is the situation on the sphere. Well, actually, there are flows where not every geodesic intersect, and well, here we have a complete answer, because if these two do not intersect, this always works, we have non-left-handedness. And if any two intersect, then actually we can relate the linking number in the unit tangent bundle to the intersection of the surface and prove that this is left-handed. Okay, but I'm not going to describe that in detail. What I would like is to say what happens in negative curvature. So now let's go to negative curvature. So if we go to negative curvature, we are considering, so for example, a surface here, okay, and we are considering the unit tangent bundle to this surface. And we need this unit tangent bundle to be a homology sphere. And actually, this unit tangent bundle is never a homology sphere. So it makes no sense to speak about left-handedness here. So then you will say that, yes, then we cannot consider this geodesic flow from this point of view. But actually, we can mod out these things. We can consider not surfaces, but orbifolds. So let me describe what an orbifold is. An orbifold is an orbisurface, actually a two-dimensional orbifold, is like a surface, but just it has conic points. So this is a topological surface here, with some metric, which is locally just a standard metric, except at a finite number of points here, 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 where it's not isometric to a disk, but it's isometric to the quotient of a disk. So here you imagine that you have your disk, and you quotient that by a finite order rotation, here of order 6. So this gives you, so if you have a metric on your surface everywhere, and here locally you have not, well, you have a metric, but locally you are isometric to the quotient of this matrix by an order 6 rotation. I claim that here you can still define a unit tangent bundle and a geodesic flow. So how you describe the geodesic flow? First, well, everywhere you can just follow the geodesics, and around this conic point you can just define the geodesics in the lift here, and then project back to the surface. So here, if we have order 6, if we travel along the geodesics, we arrive here, then we go straight, but then by the order 6 rotation, it means that we go back here. So we go here and here. This is described as geodesic flow. And if we come close to that point here, well, in this disk we come close to that point, that's all. But then on the surface, this means that we wince 2 times around this point that we can see here. We cross here, we wince once, twice, and then we go away. So here we can define a geodesic flow on this thing, which is locally either a surface or a quotient of a surface. Now we can also define, well, the unit tangent bundle to such a surface. And how do we do that? We just do it locally. So around a regular point, this is just as usual. This neighborhood cross a circle, the circle of all possible directions. And around this conic point, well, we just mod out by the rotations by which we are quotienting. So here, a rotation acts on the point by sending this point to that one, and to that one, and to that one, and to that one. But it also acts on tangent vectors. If you have a tangent vectors here, you just rotate it by the rotation. So what that means is that if we look locally at the unit tangent space to a disk, and we can look at how rotation acts on this disk, and it acts by rotation on the basis and by rotation on the fibers, because it rotates vectors. So here on this full torus, which is the unit tangent bundle to a disk, we have an action by screw motion, which corresponds to a rotation on the basis and a rotation in the fibers. So actually the quotient is a nice manifold. So just since the action here is proper and free, we have a quotient which is still actually a full torus, and so we can define a unit tangent bundle to any orbifold. And now what is nice is that, well, we know many examples of orbifolds for which the geodesic flow here will be an Anosov in negative curvature. So here the picture you have probably already met. It corresponds to a tiling of the hyperbolic plane with here rhombi, okay, where the angle here is 2 pi over 7, pi over 2, pi over 3, it doesn't work really well, pi over 3 here, pi over 2. So here you can get an orbifold by identifying this side here with this side here, and this side here, the horizontal one, with this side here. So when you do that, you obtain a sphere. So you are just taking this rhombus here, and you identified this side here and this side here. So what you get is actually a sphere with 3 conic points of order 2, 3, and 7. So here, if we take the hyperbolic plane with this tessellation, and we mod out by the group, by the symmetry group, what we obtain is an orbifold with 3 singular points. And now we can consider the geodesic flow on this orbifold, as I defined before, and this just corresponds to the quotient of the geodesic flow on the hyperbolic plane. Okay. So what this tells us is that, well, and this is not particular to the choice 2, 3, 7. Actually, we can start from any fundamental domain and define the geodesic flow here. And the fact that we have points of finite order is not a problem for defining this geodesic flow. And now we get plenty of examples of geodesic flow where on unit tangent bundle that are homology sphere, namely if the basis here is a topological sphere with finite order points of order P1, P2, P3, etc. So here we can consider a sphere, so I write genus 0, and some conic points of order P1, P2, P3, etc., Pk. And for each such collection, we have an hyperbolic metric on this orbifold. We can consider the geodesic flow, and this gives an example of a flow. And as soon as here we have a basis with genus 0, this will be a homology sphere. And so we can ask the question, is the geodesic flow on this sphere left-handed or not? And the statement, well, and here we can explain. The statement is as follows. The statement is that the geodesic flow on this tangent bundle, so a sphere with point of order P1, P2, Pk, yes, is left-handed if and only if k equals 3. So actually here, this works, we need at least 3 punctures. If we don't have at least 3 punctures, we don't have an hyperbolic metric. So here I should say that here we put an hyperbolic metric. So we have a surface, an orbifold here, with an hyperbolic metric. So having an hyperbolic requires k at least 3. And we have a left-handed flow if and only if k equals 3. So this theorem goes in 2 directions, because first it tells you that we have infinitely many geodesic flows, because actually, so for any choice of P1, P2, P3, actually we need a condition like 1 over P1 plus 1 over P2 plus 1 over P3 smaller than 1. So there are infinitely many choices of integer here, P1, P2, P3 satisfying that. And for any such collection, we have an orbifold and the flow is left-handed. And on the other way, if we have more than 3 conic points, the flow is not left-handed. So the proof that the flow is not left-handed for k at least 4 is very simple. It mimics the other one. The point is that if we have a sphere with many conic points, we can find geodesic that will not intersect. We can find a geodesic that stays in this region here, gamma 1. We can find a geodesic here, gamma 2, that stays away from gamma 1. And actually, if we lift these geodesics and choose the orientation in the way we should, well, if we choose the orientation, we can get either positive or negative linking number. So here, for k at least 4, we get non-left-handed flows. And for k equals 3, we have a left-handed flow. And well, I will not have the time to describe the proof here, but the proof here of this theorem, so what we have to do in order to prove this theorem is to prove that any 2 asymptotic cycles are negatively linked. And here, since we have an hyperbolic flow, actually asymptotic cycles are shadowed by cycles corresponding to periodic orbits. So the statement corresponds to say that any two periodic orbits are negatively linked. And how do we do that? I will just show a picture. We do that by controlling the topology of the periodic orbits. So first, we have that we can describe this unit tangent bundle to a sphere. We can describe it by a surgery presentation on S3, which means that here we have the unit tangent bundle. So this is our orbifold with 3 conic points. So the unit tangent bundle is just the product of this thing. So if we remove the conic point, we get an open sphere with 3 disks removed. So the unit tangent bundle is just the product of that by a circle. And this can be made effective by choosing a vector field here and then making the product of this surface here with a circle. Okay? And if you have a tangent bundle at one point, here you have an origin that is given by the tangent vector here. And then if you rotate this vector, this will describe the full fiber of this point. So here what this tells us is that if we remove these 3 conic points, what we have is the product of this pair of pants with a circle, which correspond here to the exterior of this link in the 3 sphere. Because you just rotate around the grid and not here, and this is the product of that by S1. Okay, now if you make a twist along this disk here, what you get is what is called a Hopf link in S3, and this is more symmetric because you have the symmetry between the 3 fibers. So if you remove the 3 conic points, the unit tangent bundle is just the complement of this Hopf link in S3. And now, well, this is something that has to be checked, but gluing back the points here amounts to what is called a P surgery, well, P, Q, and R, where P, Q, and R are the 3 order of the points, on this unlink. So what it tells you there is that you can present this unit tangent bundle just as S3 minus when you remove some tori and you glue them in a new way. And now this will help us. So now if we have a knot here, or 2 knots in the unit tangent bundle, we can try to draw them in S3, like that. And in order to compute their linking number, we will just have to compute their linking number on the pictures and add some term that correspond to the fact that here we have to glue some tori differently. But if we can have a picture on how the geodesics looks here outside this thing, this will allow us to compute linking numbers. And now comes the relation with the first picture of a Lorentz template, is that actually what we can prove is that the geodesic flow here can be distorted on a template. So here this is the same Hopf link as before, so with 3 components, red, blue, and green. And actually what we can prove is that you can take the geodesic flow and you can distort it, you can push it, in order to make it live on this template. So what is a template? It's just, as is here, an embedded surface made of ribbons here. Here's a ribbon, here's another one, here's the third one. Yes. These ribbons comes with a direction, so with a flow. Okay, and they are glued here. They are embedded in our manifold, and they are glued along some axes here. Here they are glued together. So this defines actually a semi-flow, because on this axis you have 2 ways of going back along the green or along the red thing. So here we have an embedded surface with a semi-flow, and so we can look at orbits of this semi-flow. And this picture looks very similar to the first picture of a Lorentz template, and actually the notions come from the Lorentz template. So now what is the statement? The statement is that you can, every periodic orbit of the geodesic flow on this unit tangent bundle can be distorted on a periodic orbit of this template. So a periodic geodesic on this orbifold is a curve that goes like that. And actually, you know that, well, you may know that closed geodesics are dense in this unit tangent bundle. So actually, they live in the whole manifold. But what you can do is to distort all of them simultaneously to make them live here. And this distortion is an isotopy, which means you don't change the linking numbers and so on. So now what you have to do in order to prove the theorem here is to take any 2 orbits of this template and to prove that their linking number is negative. Yes. And then explained, what is the linking number between two periodic orbits of this template? The linking number is just the visual linking number, which corresponds here. Here we will see some crossings, plus some terms that comes from the intersection with this, with the linking number with this hub fiber. Okay, I don't detail the proof, but then this is a lengthy computation, and you prove that any two orbits are negatively linked, and then you have, well, a bunch of examples of left-handed flows. Okay, I stop here.